Good day, everyone. Welcome to Direct Stars. Our subject for today is physics, while our topic is nuclear decay equations. Aim of the lesson is for you to understand the concept of nuclear decay equation, and objective of the lesson is for you to know what a nuclear notation is and the type of decay equation. Let's dive into the context. Nuclear equation. Nuclear radioactive decay equations show the changes in mass and charge of the nuclei in the decay itself. So each term will have what we call chemical symbol of the element or the type of radiation. We have this: A, X, Z. While A represents the mass number, which is the addition of the neutron and the proton number in the nucleus of an element. While Z is just the proton number, also known as the atomic number of that element. While X, it represents the chemical symbol of the element itself. So, nuclear notation, these are the nuclear notation. A equals to the mass number, Z equals to the proton, and X is to the element. Now we go to alpha decay equation. What does that mean? In alpha decay equation, when alpha decay equation occurs in a parent nucleus, it tries to decay at 4 and 2. What does that mean? It means that it tries to extract 4 from the parent nucleus and extract 2 from the parent nucleus, the proton number of the parent nucleus, and 4 from the mass number of the parent nucleus to have it on its own before it gives the daughter nucleus. So, in nucleus equation representing alpha decay, the nuclear number of the daughter nucleus is 4 less than the parent, while the proton number of the daughter nucleus is 2 less than the parent. What does that mean? It means when we have a parent nucleus, which is A, Z, this. So when alpha decay occurs here, then that will be, we subtract 4 from the mass number of the parent nucleus, that would be the daughter nucleus here, and we subtract 2 from the proton number of the parent nucleus to give this for the daughter nucleus. Then we add it to the alpha decay itself, which is 4 and 2. Now we can see that this equation is balanced. A minus 4 plus 4 will still give us A. Z minus 2 plus 2 we still have our Z back. So that is alpha decay equation. Let's move to the second one, beta minus equation. Beta minus equation is when we have A, X, Z. At this point, when the decay occurs in this parent nucleus, it gives daughter nucleus in a way that the mass number remains the same. The mass number of the daughter nucleus remains the same as the parent nucleus. So let's say we have Y to be the daughter nucleus, but the addition of 1 is given to the proton number of the parent nucleus, which is Z plus 1. So because beta minus occurred here, then beta minus will be, it has no mass number, that is 0, and it has minus 1, that is why it is beta minus at its own atomic number, that's the proton, minus 1. Now you can see that this equation is balanced. Z plus 1 minus 1 will give us Z. A plus 0, we still have A. Now we go to beta plus decay equation. In beta plus decay equation, when we have A, X, Z, in beta plus decay equation, here, we still have the same mass number of the parent nucleus is the same to the daughter nucleus. We have A, where the daughter nucleus will be Y, while this is Z minus 1, Z minus 1, plus. So beta plus has mass number of 0, and it has plus 1 as its own proton number. That is beta plus. So you can see this is balanced too. Z minus 1 plus 1 gives Z. Z plus 0 will still give us A. So we go to the last one, which is gamma decay equation. Gamma decay equation, here, the proton number and the mass number still remain the same for the daughter nucleus. But gamma decay equation deals with electromagnetic waves. So gamma decay equation doesn't have mass number and doesn't have proton number. So when we have A, X, Z, here, The daughter nucleus will still remain the same mass number, which is this, and the same proton number, but gamma decay has occurred there, which is 0 mass number and 0 proton number, because gamma decay doesn't have a proton number or a mass number. It is electromagnetic waves. So let's solve a question to denote everything there. So we'll go with this question here. The question is, show all the nuclides of 23792W in decay equation. So when we have 237W and we have 92, so here when alpha decay occurs here, okay, when alpha decays occur here, it means that this will give out a daughter nucleus of 237 minus 4. Then we have X to be the daughter nucleus, and this will be 92 minus 2, okay, plus alpha for 2. So 92 minus 2, that would be 0. And 237 minus 4, that would be 233. So we have 233 here, and we have 90 here. So that is alpha decay. What about beta minus? To go to beta minus, we have 237, 92, W. That will give us, in beta minus, the mass number remains the same. So we still have 237. Then we have daughter nucleus. And 92, in beta minus, the proton number is addition of 1 to the daughter nucleus. That is 93. Then we have beta minus. That's it for beta minus. Now let's go to beta plus. Beta plus, we still have 237, 92. So here we have beta plus. That is, it will give out 237, the same mass number. Then we have Z here. Let's have Z here as a parent, the daughter nucleus. And we still have 91 here. So that will give us B0 plus 1. So that's 91 plus 1, we still have 92, 237 and 237. 237 plus 0, we still have 237. We go to the last one, which is gamma decay equation. So when we have 237, W, 92. In gamma decay equation, here, the daughter nucleus still remain the same as the same proton number and the same mass number. Let's add that to be P, which is the daughter nucleus, that is 92. Then gamma decay equation occur there, 0 and 0. So this is how to show all the nuclide in decay equation. So that will be the end of today's class. Thank you for watching. Don't forget to click on the subscribe button and like this video. Bye. See you in our next class.